Hi, thank you for spending the time watching this video. I'm Jiale. I'm going to talk about stable matching with interviews, which is a joint work with Itai, Mohammad, and Amin from Stanford University. In this work, we're going to solve the interview congestions in two-sided markets. Agents in real-world markets, including labor and dating markets, often lack clarity about their preferences. So mutual interactions, for example, interviews, are essential for gathering information and refining these preferences, which might lead to interview congestions in markets. For example, in medical residencies market, programs handle significantly more applicants than available positions. In dating platforms, most online conversations fail to result in in-person meetings. However, many existing models overlook the role of interactions in preference discovery. They mostly assume perfect information about agents' preferences. And in this work, we're going to model the incomplete information about agent preferences and minimize the number of interviews while ensuring good outcomes. Here is the model setup. There will be n applicants and n positions. Applicant I will have a publicly non-value U sub I, and position J will have a publicly non-value V sub J. Applicant I's pre-interview utility with respect to position J will be the position's public value V sub J. And similarly, position J's pre-interview utility with respect to applicant I will be the applicant's public value U sub I. In our model, there is an interview stage for preference refinement. After interviews, the subjective interests of both applicants and positions will be reviewed and will be used for refining their utility. More specifically, applicant I's post-interview utility with respect to position J will be the publicly non-value of the position plus the subjective interest of the applicant. Similarly, position J's post-interview utility with respect to applicant I will be the public value of applicant I plus the subjective interest of position J. In this model, the solution we're going to find is called the interim stable matching. A matching is a set of vertex disjoint edges. And a matching is called interim stable if all the matched pairs have interviewed each other and there are no blocking pairs with respect to the observed utilities. The definition of a blocking pair is the following. Denote mu of A sub I as the matched position of applicant I, and mu of P sub J as the matched applicant of position J. Then, an applicant position pair A sub I P sub J is a blocking pair if, according to the observed utilities, A sub I strictly prefers P sub J to its currently matched position, and P sub J strictly prefers A sub I to its currently matched applicant. So the blocking pairs are defined based on the observed utilities, and the observed utilities are defined based on the pre-interview utility and post-interview utility in the previous slides. For pairs that have not interviewed each other, the observed utilities are the pre-interview utilities. While for pairs that have already interviewed each other, the observed utilities will be the post-interview utilities. So this is a definition of an interim stable matching that we want to find in this model. A trivial approach for finding the interim stable matching is the following. First, we ask all pairs of applicants and positions to interview each other. And then we find a stable matching with respect to the observed utilities. And since all pairs of applicants and positions have interviewed, the observed utilities are post-interview utilities for all of those pairs, and a stable matching is exactly an interim stable matching in our model. The bad thing is it will introduce interview congestion, meaning the vertices will have degree n in the interview graph. Now, the first result of our work is an adaptive algorithm with degree log n squared. Here are some assumptions we make in our model. First of all of those subjective interests are independent. Also, the subjective interests of the positions are sampled from the same symmetric distribution with mean 0. Similarly, we have the same assumption for the subjective interests of the applicants. Note that the two distributions here do not have to be the same. An adaptive algorithm can base future interviews on the outcome of the previous ones, meaning that it can look at the interview results of the previous interviews and decide its future moves. Before showing the detail of our adaptive algorithm, let's introduce the classical Gale-Shapley's algorithm in the model with complete information of preferences. In Gale-Shapley's algorithm, while some applicant is unmatched, the algorithm will pick an arbitrary unmatched applicant A sub I. And then it'll look at beta of A sub I, which is the most preferred position from which the applicant is not rejected yet. Now, suppose the position is not matched. The algorithm will match the applicant and the position immediately. On the other hand, if the position has already been matched to an applicant A sub I prime, and also it prefers A sub I to its current match, then the position will reject its current match and the algorithm will match A sub I to beta of A sub I. Otherwise, the position will reject the applicant immediately. Here is the illustration of how Gale-Shapley's algorithm work in our model, but with complete preferences, meaning there will be no interview phase. In the algorithm, it chooses an arbitrary unmatched applicant, let's say the second one, A sub 2. And the most preferred position of A sub 2 is P sub 1. Since P sub 1 is unmatched, the algorithm matches A sub 2 and P sub 1 immediately. In the next step, let's say the algorithm chooses A sub 1. And similarly, P sub 1 is also the most preferred position of A sub 1. But in this case, P sub 1 is already matched to A sub 2. However, it prefers A sub 1 to its current match. So P sub 1 will reject A sub 2, and the algorithm will match A sub 1 with P sub 1. In the next step, let's say the algorithm chooses A sub 2 again, And in this case, P sub 1 has already rejected A sub 2. So the most preferred position of A sub 2 becomes P sub 2. And since P sub 2 is unmatched, the algorithm matches A sub 2 and P sub 2. The algorithm will end when every applicant is matched to some position. And at that time, the algorithm will output a complete stable matching. Now we're going to modify the Gale-Shapley's algorithm for our model with incomplete preferences. We need to make 3 modifications. The first one is, since our preference is incomplete, before matching the applicant and the position, an interview must be conducted. And then we will carefully choose the pair of applicant and position for each step. And finally, we will reduce unnecessary interviews. Let's focus on the points one by one. Suppose we choose our applicant A sub I and the position beta of A sub I, and we try to match them. If we find out that the applicant and the position haven't interviewed each other, we will conduct the interview and update the observed utility of both sides. For carefully choosing the applicant-position pair, we will consider the applicant set capital A, which is defined to be all those unmatched applicants such that beta of A has the smallest index. In other words, their most preferred position that hasn't rejected them has the largest value, largest publicly known value. And we denote J as the index of that position. The applicant in this round will be chosen as the favorite applicant of P sub J in the applicant set A. And the way we're going to reduce unnecessary interviews is that before actually conducting the interview, let's look at the applicant's the current applicant and position. Suppose that the position has already been matched to some applicant A sub I prime, and also it prefers A sub I prime to A sub I with respect to the current observed utilities. Note that the observed utility with respect to A sub I is the post-interview utility, and the observed utility with respect to A sub I is the pre-interview utilities. In this case, we can reject A sub I before conducting the interview. Now here is an illustration of our adaptive algorithm. Remember that we were going to look at the applicant set capital A, which is defined to be the unmatched applicants such that the beta of them has the smallest index. In the first step, the capital A will contain all the applicants, and their mostly preferred position will be the first position, P sub 1. And for P sub 1, the most preferred applicant in the set capital A will be A sub 1. So in this step, we will consider the pair A sub 1, P sub 1. The algorithm discovered that they have not interviewed each other, so an interview is going to be conducted. Let's assume that the result of the interview is not pretty good, meaning that the first applicant does not like the first position, and the observed value, the observed utility of the position becomes 3 minus 2 equals 1. So now the first applicant actually prefers the second position to the first one. And then we move to the next step. In the second step, the capital A becomes A sub 2 and A sub 3 because the mostly preferred position of the first applicant becomes the second position. So the algorithm will choose the pair A sub 2 and P sub 1 and conducts the interview. Now let's say the interview results are great for both sides. The first position remains the mostly preferred position of the second applicant, and the second applicant becomes the mostly preferred applicant for the first position. In the next step, capital A doesn't change, and the algorithm considers the same pair A sub 2 and P sub 1 again, and matches them. Then the set of applicant capital A becomes only A sub 3. And the algorithm considers the pair A sub 3 and P sub 1. In this case, P sub 1 is already matched, and the observed utility of P sub 1 with respect to the current match A sub 2 is 2 plus 2 equals to 4. However, the observed utility of P sub 1 with respect to A sub 3 is just 1. So the position prefers its current match to A sub 3 before the interview. Thus, A sub 3 is rejected without interview. Now the algorithm continues until all applicants find their position in the matching. And it can be shown that the adaptive algorithm finds an interim stable matching with high probability. And also, for each position P sub j with high probability, it will only interviews an applicant A sub I such that the index of the applicant is at most log n squared smaller than the index of the position, and also it can be only log n larger. In other words, it reduces the degree of the vertices from n to log square n in the interview graph. We also have a non-adaptive algorithm with degree log n cube. The assumptions on the subjective interests are the same. A non-adaptive algorithm works in two phases. In the first phase, it proposes a set of interviews between the two sides, but no actual interviews are conducted. In the second phase, interview results are reviewed simultaneously, and then the algorithm finds an interim stable matching with respect to the observed utility. Our non-adaptive algorithm works on markets with spectral structure called tiered markets. In a tiered market, applicants and positions are partitioned into tiers. Higher tiers are always preferred than lower tier, no matter what the interview outcomes are. And within a tier, applicants or positions will have the same public value. The detail of the non-adaptive algorithm can be found in section 3 of our paper. Finally, we're going to present an open problem. Both our adaptive and non-adaptive algorithm do not consider the strategic preference reporting of the applicants or positions. And designing algorithms with dominant strategy incentive compatible property would be an interesting future direction. Thank you.